First of all, I thank the organizers for inviting me to this conference here in Agra. Quantum computing has been around for a while and implementations of various types have been also around. The idea of doing quantum computation with mixed states has also been around for a while because mixed states is something which cannot be avoided. Most states in nature are mixed. And particularly in the context of NMR quantum computation, one knows that at room temperature, states are highly mixed. And there were a lot of discussion and critical analysis of NMR quantum computation from the point of view that states are highly mixed. And therefore, is there a quantum advantage or there is no quantum advantage and things like that. And then came this whole idea of pseudo-pure states where you begin by taking the whole set of spins in an NMR quantum computer, and then what you do is that you take some of them and a small fraction of them are pushed into a state. So you have a very mixed density matrix rho, and then you do something to it so that it becomes something into I plus 1 minus k into something which is a pure state. I have to write maybe bigger, right? Yeah. So the idea is that you have one particular state which is more populated and rest is a density matrix proportional to identity, and then you work with this part. Okay? Can people see what I wrote? No. Okay, so this is pseudo-pure state, which is a very interesting idea which came also early on in the field. However, the point is that the number of molecules which one can push into this pure or pseudo-pure state is very, very small. It's exponentially small compared to the total number of molecules in the ensemble. And therefore, it is extremely difficult to prepare such pseudo-pure states. I'm not going to talk about doing quantum computation with pseudo-pure states, but this is the only way you can do NMR quantum computation today. There has not been an alternative to this. There are schemes. I mean, this is not a fundamental exponential problem here, but there are schemes. The issue is that this is not a fundamental difficulty that one cannot have large number of molecules in a pure state. It's a practical difficulty, and lots of people have come up with schemes like optical pumping and so on, where they're able to push or trying to push a large number of molecules into a pure state, and pseudo-pure state quantum computation might also become possible soon. So, computing with mixed states. What other things do we look at in our group? We look at quantum algorithms. We also look at implementations of QIP and the theoretical and experimental problems over here. I'm a theorist, so I work with experimentalists on this. Recently, we have been looking at open quantum systems where you have an environment interacting with the quantum system, and therefore you have a non-unitary evolution of the system. And this is a very interesting area which is opened up, which has been around but has opened up in the context of QIP recently, and we also work on quantum optics. Okay, so now let's see computing with mixed states as is a particular example of Deutsch-Jozsa algorithm that I will look at. So there have been proposals recently in past 5 years or so where highly mixed states have been used to do computation, and ostensibly quantum computation. And they're maximally mixed. So something which looked like a problem here that we should not have mixed states have actually been employed to come up with quantum computational schemes. Now this talk would look at this proposal very critically and show you that at least the particular scheme which I will describe has some hidden cost which kills all the advantage it apparently claims to have. So that is the aim of this talk, to critically analyze this particular scheme to do Deutsch-Jozsa algorithm, which was the first example that took up to do quantum computation with highly mixed states. So let me just review the Deuze-Jozsa problem and Deuze-Jozsa algorithm. Here what we have is there is a function from n bits to 1 bit, and the issue is the function constant or balanced? So constant means its output is same for all values of the input, and balanced means that for half of the input values it's 0 and for the other half it is 1. So if the functions come from this particular set of functions, given a functions, how to classify whether it is constant or balanced? That is the issue in Deuze-Jozsa problem. Classical algorithms are not very efficient in this case. Let me put it clearly. Classical deterministic algorithms are not very efficient to do this job. There are classical random algorithms which we will come back to. But a quantum algorithm, which is a Deuze-Jozsa algorithm, a well-known, which is the first quantum algorithm in some sense, achieves this classification in one oracle call. So, classically, you have to have it of the order 2 to the n oracle calls, and the quantum algorithm is only one oracle call. So, it's an exponential advantage over the classical schemes. That was the point of the Deuze-Jozsa algorithm. However, let me go back. However, to do this quantum DJ algorithm, one needs pure states or pseudo pure states. It requires that the n qubits are prepared in a pure state, or at least a pseudo pure state. So this is a requirement for this particular algorithm. This is the kind of oracle that it uses. So you have, this is n qubits, this is 1 qubit, you have a unitary which encodes the function into the target like this, and then if you have all this in a pure state, then the algorithm will work in one such unitary will be able to classify functions. And pure states or pseudo pure states are required to undertake this classification. I'm not going to go into details because this is now quite standard, and if there's a question we can take it up at that stage. Now here is an alternative which has been proposed, which I want you to pay attention to. In this proposal, the proposers say that let us begin with the maximally this particular state, in which n qubits are in a density matrix proportional to identity, and the last one is 0. The last one is a pure state. Preparing 1 qubit in a pure state is not that difficult. We can do that. And all these are in maximally mixed state, which is identity, which is in some sense pure noise. And then this can be rewritten, by the way, like this, where x are computational bases, which is 0, 0, 0, 0, all the way to 1, 1, 1, 1. So then we push it through the oracle, which gives us the output density matrix like this. So here you see, since it was 0, so for every x, the fx has appeared over here. So equation 4 tells you the application of oracle on this very highly mixed input state. And now we trace over all the input registers, and the target qubit is left in this particular density matrix after the tracing, and all the information about the function appears to be contained here, which can be easily seen by making an expectation value measurement of sigma z. So if sigma z expectation on the target is plus minus 1, the function is constant, and if it is sigma z value expectation is 0, then the function is balanced. We used the oracle only once, and we used a very highly mixed state, and then achieved the same task which required pure states or pseudo pure states. So this is basically the scheme which we will look at. I also want to bring your attention to another aspect here, that we also made only an expectation value measurement. Normally quantum computation requires projective measurements, which are much more difficult than expectation value measurements, and this also has been proposed, has been claimed to be an advantage of this scheme, that expectation value measurements are sufficient to do quantum computation if you are willing to work with highly mixed states. This looks like magic. You have actually gone into worse states, and you seem to have achieved much more. So that's how we started looking at it, and there must be a catch in this scheme. The way I have been putting it, so, I mean, some of you might have already recognized that there might be a problem. So let us just to conceptualize the problem, look at a classical alternative where I look at 2 to the n classical bit strings of length n plus 1, and then I apply, what I do is first n of them, 2 to the n, these are the strings, and then I prepare them in computational basis, the first n, and the last one 0. So now it's a completely classical problem. I'm working with strings, and I keep the last bit of every string as 0, and first n bits are all possible n-bit strings, so there are 2 to the power n of them. Now if I apply the classical oracle, which means on the same string, take the first n bits as input and push the function onto the last one, then after the oracle on the whole set of strings, the fx values are there on the last bit. And then of course I can add those values and find out whether the function is constant or balanced, because that value will be 2 to the n or 0 for a constant function, and 2 to the n by half for a balanced function. But of course then you will ask me that, I use 2 to the n inputs. So basically I have used 2 to the power n oracle queries and not just one oracle query. I explicitly have put it in here. Now what I will conclude at the end is that the mixed state proposal is nothing but this. Just the costs are hidden in the algebra and not so obvious. So the exponential resource, which is explicit in classical situation, while it is hidden in the definition of input density matrix for the ensemble quantum case. And this is the issue which we will explore in detail. This deceptively simple looking density matrix, which is identity cross identity cross identity cross identity all the way, it requires of the order 2 to the n molecules to prepare in an experiment. There is no other way. It's easy to write down on a piece of paper, but if I want to say that my n qubit system is in this density matrix, and I want to use this to do computation and measurements and so on, then our claim is that you require of the order 2 to the n molecules. So therefore you have translated, so you need a resource of molecules which is exponential in n. And this remains hidden if you don't get into details of detailed analysis of this density matrix. If you just write down the density matrix and carry out the computation, this remains completely hidden. So let's look at the n qubit density matrix little further. So you can always look at rho as in terms of an ensemble decomposition, which we already did in terms of computational basis for our density matrix. So I don't have to get into this detail. So now imagine an ensemble decomposition of maximally mixed states, where first n qubits are maximally mixed and the last one is pure, and these are the ensemble members, and these are the probabilities with which they come. You see, in an actual implementation, we need to have at least one molecule from each of these members of the ensemble. So since you are going to compute f of x on every x, if I have say only a small number of molecules in my scheme, then you can see here that this ensemble itself has 2 to the n components, 2 to the power n components, and they, as a matter of principle, each component should have several representatives to give me good statistics, but at least one is required. So you see, there is going to be a problem. So now we ask that question explicitly, that let me say that I have only m molecules. So if I fix number of molecules and I try to do the DJ algorithm using the maximally mixed state protocol, so what happens? So as n increases, very soon it's going to happen that m is less than 2 to the n by 2. So in this case, more than half the computational basis states cannot find a representation in the ensemble because there are simply not enough molecules. So there is, therefore, that translated into the DJ algorithm case, there are always balanced functions which will have same value over these m states, and therefore will get classified as constant functions. So of course, constant functions will always get classified correctly, but there will be balanced functions which will get classified as constant functions because there are some missing molecules, there are some missing representatives in our ensemble. Let me make a small remark here. I quite don't know the composition of the audience, so if there are questions, they can be asked at any point of my talk. You don't have to wait till the end. So what one is saying is that, let me go back one slide further to clarify that. We are working with this particular ensemble in which this is a pure state and the ensemble is 2 to the n such states. So you need x going all the way from 0 to 2 to the power n minus 1, and then you construct a mixed state with these probabilities. Now for a realization of this state, every component of the ensemble must find a representative in the experiment. Therefore, at least I need 2 to the power n molecules. I need actually much more than that, 10 times that, or to get good statistics. But therefore, what one is saying is that this simple looking ensemble is something which requires a very large number of molecules for us to seriously be able to say that indeed we are working with that density matrix. That's the point I'm making. I hope I have clarified. Okay, so now this is actually puts it more explicitly. Now if you have a fixed number of molecules and you keep increasing n to see the scaling, soon you will run out of molecules in the sense that there will be some balanced functions which will get classified as constant, and therefore there will be an error. And now I will take you through, then you do counting, and counting reveals that you can count that number. So if you have m molecules which is less than 2 to the n, which is capital N, then the number of balanced functions classified as constant is this. So you divide it by the total number of balanced functions and the failure fraction which you can compute for this particular scheme. So now even if you, but this is ideal case where you have 2 to the power n molecules or m molecules, and each one of them is in a different state. But in a real experimental situation, you can't really ensure that. So this is the best case analysis. This failure fraction which we calculate here is the best case scenario. In reality, the situation is going to be worse because each molecule is not going to be in a different state, and therefore there are going to be further errors because of statistics, of the bad statistics, because we don't have a big enough ensemble. So that is something which is a further, but we will continue with this best case scenario. Well, the oracle for the mixed states can be rewritten very nicely in this form with these projection operators, which is useful for our analysis. And then the probabilities for the output can be computed nicely in terms of this trace over the target qubit. So all this is the machinery which we can use. Now I come to an important point, because one can argue in a slightly different direction also. In this particular Deuze-Jozsa problem, since the answers are 0 or 1 for a constant function and say something like half for a balanced function, there is a gap. So you can say that there is a gap which will save me, and even if I have less number of molecules, then I can maybe work with them. Maybe I should indicate that over here. So final expectation value of SZ when it is measured, this will be plus minus 1 for a constant function, and it will be 0 for a balanced function. So then I can argue in the following way that since constant functions live here and here at plus 1 and minus 1, so even if there is error, whatever appears here, even if it is not exactly 0, I will keep calling it a balanced function, and this might help me to save this scheme. So then we have to do this analysis with a accuracy. So what we say is, let's assume that if there is this error R over here, so if there are R molecules on which we are getting a wrong answer, we give you that freedom, because that if that R is small, I can always say that, you know, anything less than, so whatever is here is a threshold problem. Whatever is here below 1 minus R, we will push it to 0. Whatever is above minus 1 plus R, we'll push it up. So whatever, so all these measurements will club into 0, and therefore these will be balanced. And whenever I hit these values in this range and in this range, I will coarse grain and put it up here and here and call that constant. So we allow this certain amount of error tolerated, and we so R by M is the fraction. So if the total M molecules I'm using, then I allow a freedom of R by M to be accommodated in a situation like this. So now I have a very realistic situation where I have a fixed number of molecules, and I have allowed you certain amount of error, and then we will go ahead and ask the question, what is the probability of success of this protocol, giving it this chance to survive with this finite accuracy? And that calculation is slightly involved, but finally we get a nice answer, and we are able to get the failure probability as this. And the best situation is when your detectors are so good that you can measure up to single molecules. So when signal from a single molecule can be picked up, that is R equal to 1 case, the P failure is this much. This is the best case. This is the cases depending on what is the accuracy you have for your measurements. Now, one other aspect is that for the Dojos problem, one has a classical random algorithm, because once you're allowing errors, you're not working with a deterministic system. So therefore, the mixed state density matrix formulation should actually not be compared with the deterministic classical algorithm. It should be actually compared with the random classical algorithm. And those results are known. If you have a random classical algorithm for Dojos, what does it give you? So you can calculate the failure, classical random algorithm failure probability, which is here. And then you get this final result, which we have a clear bound on the relationship between classical failure probability. This is just an intermediate step, because to prove our bound, there's an inequality which we needed. So the probability for failure of the mixed state algorithm is definitely always larger than the classical random algorithm. So this is our conclusion, that this hidden cost, when it is put in explicitly, kills all the advantage and makes the failure probability greater than a classical random algorithm, because that is also understandable intuitively. I mean, even if one does not have an inequality, because the quantum mixed state algorithm will become equal to this one in the best case scenario, where you do not allow statistical errors. You only allow errors because of fixed M. Because in the classical one, we have full control. We generate a random number and we keep it only if it is different from the previous one. If it is same as the previous one, we throw that case. And the throwing cannot be done in the quantum density matrix. So therefore, it always performs worse than the classical counterpart. So thus the probability of failure for this is always strictly less than that of version discussed, the classical stuff. So then what are the conclusions? So the first issue is that it's all to do with interpretation of the density operator. So once I have a density operator, how do I interpret that? Of course, there are two ways of interpreting a density operator. One being an ensemble interpretation, another being a single particle interpretation, where you say that density operator is a single object is in a very highly mixed state. And that is the point of view which the proposers of the scheme had taken, without realizing that any verifications will always involve an ensemble, and therefore there is no way out than to consider an actual ensemble and its size and so on and so forth. For a single object, when I say that its density operator is I, or it's maximally mixed, I basically express my ignorance. I basically express my ignorance in the sense that I am saying I don't know the state of that object. And if I am only expressing my complete ignorance, I don't think that that can be useful. And that's what is happening in this case. Whereas if you are completely ignorant about a large number of objects, then you can at least work with the statistical distribution, the ensemble distribution. But that is then completely classical. You're saying that you're choosing this much fraction in this component of the ensemble, this much fraction in this component, so on and so forth. So therefore, the lack of purity of a single quantum system cannot be useful. It is basically lack of information. So therefore, it can only add to noise. That's one thing we'd like to say. So one has to interpret density matrices or density operators properly. Then there are other schemes which are around where one thinks about simulating quantum systems using mixed states. Now our results have no bearing on those schemes, because it's not that the mixed states are completely useless. In the case I discussed, they turned out to be useless, because when quantum superposition and classical probabilities intermix, one doesn't really know what happens. For example, one has an open problem of characterization of mixed state entanglement. So therefore, it is still an open question. We have not clinched the matter that mixed states are completely useless. We have looked at one scheme and have done a complete quantitative analysis of that scheme and showed that there's a hidden cost. But there could be possibilities where the hidden costs are less than the advantage which you get, and that issue still needs to be explored, particularly when you're trying to simulate quantum systems, because if you're simulating an open quantum system, for example, it is known that mixed states can be quite useful. There are results we have in a different direction which show that mixed state input states for a open quantum system can actually be useful and make things more efficient. So there can be problems in which mixed states can be useful. Therefore, power of mixed state QC is not a completely closed question. There are still issues to be sorted out there. However, what we have shown is that the naive schemes which people have come up with don't really work. Okay, I will end here and then take questions and discussion.